Thank you, Michael. Thank you for putting that up. Thank you for the opportunity to be here in Luxembourg. I really enjoy it already, and I'm sure I'll enjoy more of it. And thank you for the chance to be part of the conversation. So this is what I'd like to talk about, flexibility in infrastructure design. And the theme today is that really we are changing the paradigm from designing to specified requirements to the actual conditions using flexibility. That is our challenge. And let me then that the reason we want to do it, what? You need to do this. Oh, sorry. I hate being tied down, but I wish they were more flexible. So using flexibility in design, it is possible to increase the expected value from a project easily on the order of 20, 30%. Sometimes it's less, sometimes it's more, but these are within the range of possibilities. But note, I've talked about expectations that is integrated over the range of possibilities that may occur. It basically uses a win-win approach that on the one hand, it mitigates the downside, and this is to pick up what Gary's been talking about, that you don't invest in big mega projects, you invest incrementally, so if the future is not as ambitious or as glorious or as demanding as you expected, that you have not overbuilt. But on the other hand, you're not locked into a particular size that you can incrementally adjust and take advantages of the increased demand or new opportunities that may exist. So that you have a win because you can lose less and a win because you can achieve more and consequently increase the overall expectation. Now, so what I would like to talk about is, on the one hand, to put this in the context of the established procedures for the design of engineering systems. And I think we need to really take that into account. Secondly, to take into account something that is very simple, which is the so-called flaw of averages, to understand that if we don't look at the distribution, we will make mistakes. Building upon those two, to talk about what the concept of the alternative paradigm is, that is the paradigm of designing for flexibility. To briefly suggest the analytic procedure, because this is not a lecture to students, but just to sort of point out the elements of it. And then have a example application to sort of show you what I mean. So what is a standard procedure for designing engineering systems? This is the image here, a textbook image from one of the systems engineering handbooks, and it represents one view, but a very standard view of the way we think about the engineers, the engineering professions. I am an engineer. Think about it. It starts in the upper left-hand corner. It says, define the requirements. I mean, it's very natural for the engineer to say, all right, you want me to build a road? What do you want me to build? I am the engineer. I design highways, whatever. I'm not an economist. I'm not a sociologist. I'm not in urban planning. I cannot think about those things. Those aren't my realm. Tell me what you want me to build. So step one, define the requirements. Then you look at the overall concept, the details, the more details, and you put it all together, and you've fielded the system. This is the standard textbook thing. Step one, define the requirements. Now, the assumptions of this is, first of all, that the companies, the public, know what the needs are going to be. As if you're going to say, I need a 4-lane highway, it presumes that you know that you need a 4-lane highway. That's what's required, not only in terms of capacity, but in direction, and so forth. That these requirements are time invariant. We've defined them now, and they're not going to change. That the product or facility can be designed as one coherent whole and built and deployed in one step, as we built a 4-lane highway. We don't build a 4-lane highway that might be a 6-lane highway or might have a bus lane, separate bus lane down the middle of it, or some other facility. That we're only doing one at a time. We designed this road, not a network of roads. And the system will operate in a stable environment as far as the regulations are concerned, the technology, the demographic, and usage patterns. These are the standard assumptions based on the idea that we can define the requirements right up front. Now, what are the facts? Do we know the needs? Certainly not. New ones are always emerging. whether it's technologically or sociologically or politically or whatever it's driven, new ones emerge. Are the requirements fixed? No, they change. Can the system be deployed as a coherent whole and employed in one step? Generally not. Even if we build a 4-lane road, for example, we'll think about we might need more exits, that we might need some service facilities along the way, that we want to expand it in a particular way, that we want to create bus lanes or whatever. We change things. Is only one system going to be built? No, we're probably going to build families of it. We think about the, say, a communication system or solar PV system. We are going to build many of them likely, even if we only designed one at the beginning. Will it operate in a stable environment? We could only wish for such a thing. So the point being is that the basic assumptions behind the engineering practice, which is define the requirements and we, the technologists, will design it, is not well-founded. So I don't want to recognize that traditional systems engineering has been very successful. I mean, what we have managed as societies to create over the last 50, 60 years are absolutely incredible. I mean, complex aircraft that fly long distance, IT systems, you name it, there are incredible developments. So from a technological point of view, there's no question that we have been enormously successful in the kinds of things that we've done that were inconceivable when I was beginning my technological education 50 years ago. That's not the point. It's not to say that we haven't been very successful in the terms we set for ourselves. But we can now do a whole lot better. And one way to do it is to step outside the box of our assumptions. As we're in the box of thinking that we design towards requirements, a silo kind of design. If we manage to step outside of it and do something different, then we can do better. And it's particularly important because this box of assuming that we can design the requirements is unrealistic. We need to do something else. So the reality that we have to deal with is our plants and facilities face great uncertainties. The outcomes of anything we design is risky or uncertain. I'm using risky in the sense we don't know what's going to happen. They may be better. They may perform better than we imagined. They may perform worse, but we don't know what they're going to do. And this is a fundamental reality we have to deal with, or a fundamental reality we have to deal with. Now, a small technical issue that's important here. Because you could think, as is implicitly done very often, is that, well, we don't know what's going to happen. The traffic may grow like this, the demand may grow like this. It may be higher, it may be lower, but it's sort of somewhere in between. And if we design for that sort of average situation, we'll do okay. I mean, it'll go up or it'll go down, but we'll be doing okay. That notion that if you design for the average, you really do okay and get the right design, that's the so-called notion of the flaw of averages. It's named, the analytic aspect of it is absolutely trivial mathematical statement known from a long time, but the notion of calling it the flaw of averages can be attributed to Sam Savage. And it's a pun. It's a pun in the sense that a flaw is a mistake, and it binds that sort of notion of mistake with that thing about the law of averages, that things sort of go towards the average, that balance out. And the flaw simply consists of assuming that an evaluation of potential designs based upon average or some kind of best guess or performance will give you the right answer. It won't give you the right answer as to value, but also if you look at 1, 2, 3, 4 potential designs and evaluate them on basis, you'll be doing the calculations wrong for each one of them, so your ranking of the designs will be wrong, and your choice of designs will be wrong. That is the essence of the flaw of average. Here is a graphic to sort of suggest it. Here is the drunk walking down on the road, staggering back and forth. On average, is in the middle of the road and doesn't get hit by the traffic, but guess what? He does get hit by the traffic. That's the notion of the flaw of averages. So, give you a real example here. This is a project I was involved with, and I could describe it in a slide, for the evaluation of a mine in Chile. And is based upon an economic evaluation of the mine of what is the right design for it, and here where it goes. And it had a deterministic valuation based upon the assumed best guesses of the price of the copper ore and the other metals that go along with it, and for a particular capacity of the plant, and also the quality of the ore that as it was extracted in terms of its richness in copper and other materials. And we repeated the analysis, the same data and everything, but recognizing the uncertainty that, yes, the quality varied and the price varied and so forth, and the results are very different. Let me give you this example from a mine in Chile. And to give you a reason for why the differences are so great, the fact is that given a fixed capacity design for the most likely value, if you wanted to produce more, or you could produce more because the ore extracted had a higher percentage of copper in it, or because the prices are high and you really wanted to capitalize on this by sweating the investment by working overtime, you were limited as to what you could do. So excursions in terms of more profitable opportunities were limited. You couldn't do it. On the other hand, if excursions are below the averages in terms of the ore isn't very good quality and the prices are terrible, you certainly could hit those, so that you were limited on the upside, but you could hit the full force of the downside. So here's the difference. The original net present value without the variability was 1.8 billion. When you did the analysis, just assuming that you examined the simulation, you simulated 2,000 different scenarios of the way the copper prices could have the excursion and the way the quality of the ore could be, the actual value with that design was some 40% less than it actually was. That is simply not taking into account the distribution of possibilities leads you to a totally wrong assessment whenever you have systems which are not linear, convex and linear. And, bless us, almost all systems are constrained, are non-convex, non-linear, discrete, and so forth. In other words, if we work on the averages, we make mistakes all the time. So the practical consequences that unless you work with a distribution, you get the wrong answer for any evaluation, and consequently you're likely to get the wrong choice of design because your evaluation process is flawed. So a design for a realistic description of the situation differs greatly from the design on the averages, from looking at a set of requirements and a single assumption. And this is simply because when gains when things go well do not balance out the losses when things don't go well. Sometimes they're more, sometimes they're less, but they're different. So you need to look at the whole situation. So what is the concept then of the alternative design? It's really very simple. It is, first of all, that you recognize that there is uncertainty. You need to be modest about what your understanding of the future will be. You do not, if we're thinking about designing a water supply system, where my colleagues and I are doing some work on this for water supply in Asia, we don't know how many people will be part of this mass migration from the countryside to the cities in China, for example. We do not know how much what their water consumption rate would like to be, depending upon the washing machines or the things that they might or might not have. We don't know about the availability of the water that might be there. So it's an example that we simply don't know what the systems we're designing today are going to be doing 10, 20, 30, 40, 50 years from now. We just don't know it. We have to recognize that we do not understand that in any detail. that therefore we need flexible design to create systems that can easily be adapted to the future as it actually is. They can be adapted by being able to add capacity at the right place at the right time, by being able to change function. Maybe that right-of-way that you thought was going to be for a highway should actually have a mass transit system going down the middle of it, or be used for other practical purposes also. And that traditional design often leaves us with facilities and operations that are poorly suited to what is actually happening and are therefore inefficient. So the flexibility approach, I think, can lead to great increases in expected value. That is because you can adapt situations. You can, on the one hand, often avoid the downside. Simply, if you do not overbuild such a large facility at the beginning, it is perfectly possible not to have large losses if the demand doesn't turn out to what you've been doing. I've been looking at actually some LNG plants for South Australia, where the whole push for the design is to build a large plant that will have economies of scale and be great, but if the market doesn't develop, then you have a large plant being extraordinarily expensive because there's very little throughput through it. On the other hand, you can profit from new opportunities. That is, if you build it flexibly to expand not only in terms of size, but in terms of where you place your activities, you can take advantage of opportunities at different levels of demand and locations of demand. And finally, generally speaking, because you start more modestly in terms of function and capacity, that you reduce your initial capital expenditures when exactly you have the greatest risk, you don't know what's going to be happening. So that you have lower capital expenditures, and the whole thing gives you to higher returns at lower cost, and it's a great formula. It's getting more with less, exactly the kind of thing that Gary was talking to us about. The analytic procedure, I'm not going to go in detail, that would be appropriate for this, but simply to say, step one is recognize the uncertainties, do your best you can for that. Step two is then to think about what are the possible range of scenarios. I'm not just talking about one or two, but you would like to think about the variability of price paths, and using Monte Carlo simulation, you can do this 2,000, 3,000, 10,000 times, depending upon how complex your model is, but lots of times, lots of scenarios. Therefore, getting a distribution of the consequences, and therefore needing a multi-criteria evaluation, because no one metric can give you an adequate description of what a distribution is. That is, we can talk about the average, but we just don't care only about the average. We care about the extreme downside. Maybe we want to look at the upside. We want to know something about the distribution and characteristics of it. So we need to think about describing that curve, and also, of course, because there are multiple stakeholders in any of these infrastructure projects, we'd like to think about how they impact the different participants in it, the finance aspect, the user aspect, the polity, the community aspect, the governance aspect. So we need, finally, also to have an implementation. By definition, a flexible design is one that evolves over time. Over time, we add to it. We add its capacity. We change its function. We do different things. So if we want to have an effective implementation, we need to have some kind of game plan, some kind of governance plan to make sure that it happens over time in a convenient way. So integral to this technological design of what the facility is, we need in some ways a governance consideration design to how this process will evolve over time and the pieces fit together. So let me now give you an example of how this is applied. This is a real case study developed from, as you can see from this picture here, this is an oil platform with BP, and it was for a deep water facility off the coast of Africa. So I'm not supposed to tell you what the exact country is, but it ends and begins with A. You can figure it out. And it's not Algeria. And so, as typical, this original design where everybody in the business knows that we don't know a lot of things about it, was to have the 50%, the P50, the average estimate of oil in place, the standard oil in place measure, and a price as determined by the board of directors so that they would evaluate their facilities worldwide on a level playing field. So the design was given over to the engineer to design this size of facility using this price, and they set about to do it. And they're a very competent team. They did an excellent job, and they produced a single large facility which optimizes given those conditions. Now, this is the price of oil. It's all over the map. It's now down about $95 depending on where you are. It's been up to $150. It's been down in the since 2000 down to about 15. It's all over the map. The emergence of United States as an oil exporting country was not anticipated, and so forth. So that's all over the map. These are estimates of the amount of oil in place for different oil fields. And you observe the P50, the sort of midpoint of the estimate in there of two activities, and it goes from the beginning, which is where they start doing the design, to when they actually put things in through the appraisal period. And you can see that it's very easy that the amount varies enormously. It's not because God has changed or whatever mechanism has changed the amount of oil that's actually down there. It's as you understand more about the fractures of it, how you can maintain or not maintain the pressure over the field, and how much you could actually extract. Oh, and by the way, of course, the amount you can extract doesn't depend on what's down there. It depends upon the price. Why? Because you have to put some effort to get it out. And if the price is low, you don't put much effort and you cut your losses. If the price is high, then you put more effort into it. So these are estimates under assumed conditions which have yet to be factored into the various oil prices. So on the one side, on the left, if you design for the P50, you arrive at a design which is twice the amount over capacity. And if you design on the other side, is way under capacity. So you get it wrong. That's to be expected. So what we worked with them for was a platform concept, that instead of designing one single large facility, which is the obvious result if you have said, here is your problem, optimize towards it, is to say, since you don't know, let's have a family of modules. You start small. When you understand what is really happening in terms of we start pumping it out, you see what the pressure stability is and how fast the oil can seep through the material that's down there. Then you can add more. And secondly, we'll look at the subsea tie-ins, because the oil has various qualities in terms of viscosity and other things, and it often pays to be able to mix them and to pump them in a variety of ways. So if we have a flexible set of pipes that we can redistribute it on the ocean floor there, you can have better extraction from it. And so great advantages, because the single large facility is subject to very large losses if the price is not as expected, and if the volume that you can extract is not as expected. And on the other hand, the flexible design reduces your exposure to losses and increases your ability to take advantage of good conditions by expanding it. So overall, it moves the distribution of possibilities from a relatively low state to a higher state. So let me show you the figures that we developed with them, which is this. So I think this is a later. So this is the original strategies 1 and 2, which had a big facility, which, if the prices and volumes were low, could lead to large losses. And of course could have large gains as everything came up roses. So it had this distribution. And this is so a cumulative distribution of something that looked like this in terms of the distribution. And here was the expected value. And all these numbers are calibrated on 100 because we wanted to white out the details of the case. But you could see for an expected value of 100, you could have losses just as great if you, with that design. We went through a variety of possibilities, ending up with basically the strategy 8, which made you have a smaller platform at the beginning, so even if things didn't turn out well, you couldn't lose as much money because you're pretty much guaranteed to get your payback from it. And on the other hand, could expand and get much more than the others. And in this particular case, although it's not always the case, this design was stochastically dominant over the other one. That is, that the distribution was systematically higher by about 100. And the improvement in design here was about estimated at 78% in terms of expected net present value. I only wish I had 1/100th of 1% of that improvement. I would not be here today. I would own this place. I could own this place if it was for sale. So the bottom line improvement is it increased the expected value a great deal. It lowered the capital expenditure at the beginning by about 20%. This is very important because it's at the riskiest situation where you haven't started the field. You see in the startup business for this platform that you have the highest sort of implicit cost of money for it. So that's very important. So these were real results. So the flexible design is both realistic and profitable. This is the book in which with Stefan Scholtes from Cambridge University, we've tried to explain these things, and thank you very much for your attention. I appreciate the opportunity to talk with you.